Hi, welcome to Ethereal Mechanics Electrogravity. Electrogravity is the third paper in the Ethereal Mechanics series, and this video is the fourth video of electrogravity and the final video where we're going to discuss electricity. So what we're going to do is we're going to unmask Coulomb's law, and then we're going to show you that it can be derived from the already existing fields that we've talked about before. And we're going to show you the electric force model, which replaces Coulomb's law. And then I'm going to get into my normal begging and pleading section for the people that are not Patreon members. This part is going to be replaced for the Patreon folks with Patreon-only material. And then after the begging and pleading section, we're going to have an introduction to new electromagnetism V5, which is the next paper of the Ethereal Mechanics series. So let's begin by unmasking Coulomb's law. Now they call it a law. It's not really a law. It's an empirical model. You can tell by this arbitrary constant of relation here, all this blue gunk. And what I've said in the past is to see Mother Nature in her true raw form, you got to get rid of the blue gunk. And we get rid of the blue gunk by dividing both sides of the equation by Km. And so dividing force, legacy force, by Km turns it into natural force. And dividing Ke by Km results in the constant c squared, the velocity of light squared. So this is Coulomb's model in its natural unit representation. And it's interesting because what you see are charges and velocities and distances. This looks just like the fields derived from the Platonic field. Okay, but now what we're going to do here is because we're going to compute the charge from one electron, which is a second order system of protons, a SOSOP, to another electron. We're going to take the net charge of the electrons, which is QE, and so this is what it would look like in this particular situation where we're looking at the force between two electrons. So let's start off. We're going to take the inertial field model, and we're going to compute the net force on the target second order system of protons, the target electron, from a source electron, which again is a second order system of protons. And what you have here is you have source proton 1, source proton 2, target proton 1, target proton 2. These systems are separated by a distance d, and the acceleration of the source protons are given by these equations here. Basically, it's the centripetal force equations. In this particular setup here, the x and r are in the same direction here, so I'm going to interchange r and x interchangeably here. So computing the force on proton 2 from source proton 1, we plug into this equation, and the centripetal force equation, the centripetal acceleration of the source proton 1 is negative c squared over the radius of orbit. We punch that into here, and the minus sign cancels with the positive sign, and we're left with speed of light over the orbital radius. And then we have two charges, two protonic charges. There's the q squared, that's the q squared. And next we got to find out the distance. The distance is the distance on center subtracting one orbital radius and subtracting another orbital radius to get the net distance between these two protons. And that's what this is here. Now I'm going to let you figure out the rest of them. They are pretty straightforward. It's just algebra. But now to find the total net force acting on the target, we sum those two together. So this is the sum of the force on the target 1 and the force of the target 2. And we sum those together, these two terms cancel, and we're left with these two terms here. We can do some multiplication so we can combine those two here. Okay, and this is a further reduction. And then this would be the near field, well, this would be the general electric field force model in natural units. But because we're trying to get to the Coulomb model, and the Coulomb model is a far field model, they don't know if the Coulomb field holds up at the level of the quarks at those small distances. According to Platonics here, it does not hold up. There's actually a small factor. But now, getting back to, we're going to look at the field that was measured in a laboratory. 100 years ago or so. And because that was measured at a distance, it's much larger than the radius of orbit of a second order system of pretons, then we're going to basically set this to 0 because it becomes insignificant compared to this distance. And so this here is what we're going to call the far field electric force model. Okay, now the last thing we're going to do is substitute the charge of the pretons that the charge of the pretons are equivalent to the charge of an electron over 2. We're substituting this in for q squared, and voila, we get to basically the Coulomb model as we described before, exactly in natural units as it's described. Okay, so what did we learn from this? That neither the velocity nor the acceleration of the target pretons contribute to the radial. That should be the net force effect. And that the orbital radii of both systems are irrelevant, at least for the far field effects. And the orientation of the target system was irrelevant to the result. But we're going to look at in a second, we're going to look at the orientation of the source system. And this contributes to the illusion of a static field phenomenon. Okay, so only the total pretonic charge, velocity of the sources, and the distance between the systems matter, well, except for the orientation of the source. So what we're going to do now is let's look at the inertial field again, but let's rotate our source 90 degrees. And if you do the calculations like I showed last time, you end up with 0 for the net force acting on the target system. So the orientation of the source matters. Okay, so now we've just done the inertial field. Let's look at the magnetic field, see if we can't get something from the magnetic field as well. So again, let's take our 2 second order systems of pretons. Now I've colored the pretons so we can keep track of which term belongs to which preton. Okay, so here is our magnetic force model. We're going to use it in this form here. This is the same. This is an alternative representation of this because a right divide by a unit vector is the same thing as a left multiply by a unit vector. So these are equivalent representations. Okay, so what we're going to do a little differently here is we're going to compute the total source, the total force from source preton 1 on the target. Okay, so in this equation here, we need the velocity of the source. The velocity of the source is in the positive y direction of magnitude c. So there's our magnitude and our direction. And we put that there. And then we have to have the velocity of the target minus the velocity of the source. So let's go to target 1. Target 1 is moving upward, so his velocity is positive cy. And then we subtract the velocity of the source, and then we're going to add in the contribution to T2, which is c is going in the negative direction, so we have minus cy, again, minus the velocity of the source again. Okay, and this is the total contribution from source 2. You can do that on your own. So now we condense these down, we find out again that the positive cy from the target and the negative cy from the target cancel. And it leaves only the contributor of the source preton. Only the velocity and direction of the source preton matter here. So we're going to take these c's and we're going to roll it out because the c is a scalar, so we can move it out. And then we're going to condense down the y vectors here. That's what this is. And this is the same effect here. So now we want to add the contribution from both source pretons on the next page. And we're left with this guy here. Okay, so now what we have to do is resolve this Vortrix equation here. Because this is going to end up resulting in a vector. And the first thing we want to figure out is what's the magnitude. Since this is a triple product of unit direction vectors, it's basically the magnitude is 1 times 1 times 1, which is 1. So there's no contribution of magnitude. Okay, so this matrix here, though, now we're going to look at the direction. This matrix is going to rotate the vector multiplied by the right. Okay, and the way you would apply that is you read from left to right to apply to the vector multiplied on the right. If this y were multiplied on the left, then you read the matrix from right to left to apply the rotations to the vector multiplied by the left. So how do you do that? You read it this way. It says a rotation from r to y, and this is r to y. The rotation goes counterclockwise 90 degrees. So you take that rotation and apply it to y. So that basically rotates y to 90 degrees and basically ends up being the result of minus r. So we can replace this with minus r, and this is the result here. The minus signs cancel, and we're left with this here. And again, we're going to do what we did before, is we're going to replace our pretons with their equivalent of electric charge. So they're 1/2 the unit charge of the electron each. We pump those in, and voila. We're back to Coulomb's model again, exactly. So again, the same exact observations we made before. Because what we're finding out is the source orientation matters. Now let me describe this diagram to you. This is looking down on the source second order system of pretons, or the source electrons, whatever you want to say. And what we're saying here, that if our target is located off in this direction, it's going to feel a repulsive force of the effect of twice the Coulomb force that we would normally see. Because on this side we're getting both the inertial and magnetic forces are making a contribution. Okay, because right now we're adding the contribution from both the magnetic and inertial. We're doing it over all the orientations. So this was done by a computer, because there's no way I'm going to go through the millions of calculations over all of the different orientations of the source. I showed you those examples in the previous example to show you the general procedure, but now we're switching to a computer, so a computer can do it in all the orientations. Okay, so the combination of the inertial and magnetic forces in this direction give you a repulsion of +2. If our target were off on this direction, we'd have an attraction of 1. Okay, but now let's look at all of the orientations. So this is what I just showed you. Now if I take a cross-sectional cut right along here, and that would be the cross-sectional cut. Okay, coming up out of the axis of rotation, we have +1. Okay, and if I take a cut right along through here, that's what it looks like here. So this is the same lobe as this now, and this would be this lobe, these lobes here. So this is, I'm going to try to come up with a better computer animation that we could rotate to show you it's kind of hard to see the full shape of these force lobes. But this is basically what we're seeing as a combined effect. Now, an interesting thing is, it means that the electric field is not a perfectly spherical field about the source. Okay, and if we were actually to take this and spin this along that axis, okay, which would be spinning it this way, then the average force, as this is spinning, the average force felt by a target off in any direction around here, the average force over time would be the repulsion of 1/2 of what we'd expect from the Coulomb field. Now, along this axis, we would get 1. Now, if we were to spin this system in all directions, okay, the average force that we would see would be 3/4 of the Coulomb force. And this is just for the source, because we compare it to the target, because nothing matters in the target. The target always looks like a charge of 1, but the source averages over time and angle to be 3/4. So where is the missing quarter on the source? Okay, the possibilities are that there's another force. Now, I do believe there are other forces that we haven't gotten to yet. Okay, but I don't think this is it, because there's no way in all the experimentation I've done in the laboratory that I could see that I'm not off by 1/4 of a force in any of the experiments I've run. Okay, so unless there's another force out there that doesn't manifest itself in the pretonic area, in the pretonic realm where I'm measuring, that's a possibility, but I don't think so. Okay, the other possibility is that the SOSOP motion is a much more complex than I gave it credit for, because remember, the source motions do matter. So maybe the SOSOP is a lot more complicated in its motions. The other possibility is Vortrix Algebra is incomplete. I don't think so. And there's other things, there's other areas I need to complete as far as understanding what Vortrix Algebra does and understanding its full nature, but as far as being incomplete, as far as representing all the energies, I'm pretty sure all the energies are properly accounted for. Okay, and the most logical explanation is that what we're seeing is normal, and our normal experiments are blind to this missing quarter. So let's go look into some experiments. Okay, the experiment used to measure the Coulomb force was developed by Charles Augustin de Coulomb in 1784. He published the results. And again, we're using a torsion balance, which is the torsion between two charged spheres. Okay, so now the problem we have with this is we're not really measuring the field of a lone electron. In fact, in his day, they had no concept of what an electron was. In fact, they believed electricity was still like a fluid. And so the problem we run into with our knowledge today is that on this sphere that they're measuring the force between these charged spheres, these are conductive spheres. And these spheres have protons, neutrons, and electrons. And we don't just have one electron, we may have thousands or hundreds or billions or trillions, who knows however many electrons are able to get on that ball. And so we're not measuring one field of one electron, we're measuring a collection of electrons, and there might also be a contribution from the protons. And that's where we're going to be going with this, because in magnetism, I have detected that it's not just the moving charges in the wire that produce part of the magnetic field. You also have to consider yourself with the non-moving protons in the wire. And I think this effect is happening here as well, considering that the magnetic effect is also the Coulomb effect. Okay, but there's another experiment, the Millikan oil drop experiment, where they first decided to figure out, well, what is the charge of a single lone electron? And so what they did is they sprayed a whole bunch of charged oil droplets in, and one hopefully would fall through this little gap here under the influence of an electric field by two capacitive plates. And they used this experiment to quantify the unit charge of an electron. Now, remember what we said before. This is acting as the target charge. The target charge behaves as a normal unit electron. It's the source fields where the field may not be symmetrical. And again, because these are charged electric conductive plates that also have protons and neutrons, and because there's not just one charge on the source plates, there may be millions and trillions of charges on the charge plate, that we can't be sure if the field of the source is in fact spherical or not from this. Okay, and that's where we need to go in the future. But I do have one striking piece of evidence to suggest that the source field cannot be a symmetrical sphere, and that it is the non-spherical field that I've described before. Okay, and that is lightning, or discharge in a vacuum. Okay, this is where I got the picture from. They claim this is discharge in a vacuum. It looks like it is because it looks like smoke. But you'll notice that it zigzags and twists. If the source field of an electron and then the target field, if the fields were symmetrically spherical, I would expect discharges to come off in a symmetrical pattern, not these random wiggling and ziggling and vibrating patterns. This to me suggests that the electric field is not a symmetrical phenomenon. Okay, now we're going to get back to that in a second. There's another effect we have to consider. There is torque among electrons as well. It's because they're spinning systems, there is torque. And it's very interesting because the torque would be the differential force between the pretons, where we just covered the net force among the pretons, the net force being the Coulomb field. There's also a differential force, which ends up being torque. And so if we have a spinning second-order system of pretons that's stuck in this position, can't be affected, let's say it's locked down, and we put another one over here that's spinning and is able to move, well, what will happen is, under the influence of the other guy, okay, it's going to start rotating, and it's going to lock in at about 105 degrees. And this is a computer simulation of the torque between two second-order systems of pretons. And there's actually two positions where things will lock up, and it looks very much And I have data for all different kinds of orientations, and there's a lot of information. It looks very much like the quantum locking they talk about when they look at the Misner effect. I'm not quite there saying that's it for sure, but that's what it looks like. Okay, so is this the new electric model? Well, not really yet, because there's one thing we're missing here. One thing we discussed previously is that because this is the velocity of the source second order of pretons, and because we said that a source system or any second order system of pretons has to undergo process dilation, that means under velocity, this should be transvariant. For those who haven't followed, I'll explain what that means in a minute. So again, we go back to our electric discharge. You know when it first leaves, it's a very fine beam. It's held together very tightly. But as the electrons slow down, they start spreading out and doing all kinds of random stuff. This is very, very telling. And this is the same thing that happens with an electron beam in a television set, except that the electron beam is under constant acceleration because the screen of your TV set is also charged, which helps draw the electrons from the electron gun all the way to your screen, which keeps them under velocity so they don't diffuse like this. Okay, and so what we showed in the previous models is the second order system of pretons has to undergo time dilation, what we call process dilation. So as this system starts accelerating through the medium, its rotational velocity is going to slow by this effect here. And so what we need to do is we need to adjust the Coulomb model with this thing here to compensate for the fact that it's a transvariant system. Okay, for my Patreon members, this part here is going to be replaced with the begging and pleading for the people that are not Patreon members. Normally I'd put in here unreleased info. However, I am absolutely fried. Every single free moment of time, since as far as I can remember, I think going back to my summer vacation last year, has been dedicated to this effort. Okay, and I don't know if I'm going to get a summer vacation from work, and there's stuff I need to do with the house as far as maintenance and improvements to the solar power system, because we're experiencing more blackouts up here because of part shortages and whole 9 yards. I need to improve the solar power system so that we're not going to be interrupted going forward. And I'll put videos out on that because I think some people might be interested in. There's also repairs, painting, cleaning. So I'm going to take the next 2 weekends off to catch up on the things I need to get done in the summer, with hope that I do get a summer vacation this summer to complete that. Okay, now back to... So this is New Electromagnetism version 5. This is the electric force model, and this is for second order systems of pretons only. It's not for pretons themselves. These is the magnetic force model and the inertial force model. These can be applied to SOSOPs or pretons, and that's why I have changed the symbols here. The small q's represent SOSOP charges only, where these represent either SOSOPs or pretonic charges. Okay, and also right now we're going to say this is for source field contained in conductors for now until we figure out where that extra quarter comes from. Okay, and this has been slightly corrected from the version in the paper. I didn't have this notation, and I forgot to put the little s on the V in the paper. So this is a corrected form of what's in the paper. And all velocities and accelerations are relative to the medium. And to convert to legacy force, multiply each of these by Km. These two are new for New Electromagnetism version 5. This is the new induction from 20 years ago. It's just now being said for sure now. It's definitely the inertial force model, and it's being shown in its natural units for the first time. This is the end of electrogravity. This is not the end of ethereal mechanics. We have a lot more to go. So the next events, I'm going to start writing the New Electromagnetism V5 paper. This should be pretty quickly because all the experiments are done. It's just a case of dumping it all into a nice coherent paper. I'm going to shoot for completion of the paper by the end of October. And this will be the releases for the paper for the different Patreon classes and the public release for January 1st, 2023. Hopefully the video series will begin production by the 1st of December. Once they're produced, just like we're doing now, it's immediate release to Patreon passengers and above, and the public release of the videos will follow 1 month later. Thank you.